Here is our Rube Goldberg machine. It does things like this and that. Some of the energy transformations are interesting, some of them are not. They're usually not. The first one is these falling candy bars. The candy bars convert their stored potential energy into kinetic energy. Each of them weighs 37 grams, which is 0.037 kilograms. And I used that number to do a bunch of math that looks like this. I come out with velocity equaling 1.95, so V should equal 1.95 meters per second, but probably doesn't because of friction and all that. After doing a bunch of measurements and sciencey logger amateur stuff, I found the velocity to be closer to 1.76 meters per second, which makes more sense. There are 7 candy bars with identical masses and everything, so there are my 5 transformations. I'm kidding, that's a joke. Here's a rock. The rock pendulum converts stored potential energy into kinetic and potential energy. So using this here formula, I'm going to use the 120 gram, that's 0.12 kilograms, rock, and it is 21 centimeters, 0.21 meters, and then I did a bunch of math here, like that, to find that V should equal 1.48 meters per second, but that probably doesn't because friction. And after doing a bunch of more fancy logger amateur and science stuff, I found the real velocity to be closer to 1.3. Our third transformation is the golf ball ramp, where the potential energy is converted into kinetic using this here formula. And I had to look up that golf balls are, by regulation, 45.93 grams, that's 0.04593 kilograms, and this one was 6.5 centimeters off of the table, which is 0.065 meters. And I did a bunch of more maths and found that V should equal 1.14 meters per second, but obviously that's probably wrong again, and after doing more measurements and stuff, I found that it's actually closer to 1.05 or so meters per second. So this Nokia phone that falls into the cup is our, what is this one? 4th energy transformation, converting stored potential energy into kinetic energy using this formula again. To find the velocity should be 1.95 meters per second, but it's probably not. No one will ever know if it is because I can't see inside of the cup on the video. So I decided that since I almost don't have enough transformations, I would try to find, I decided that since I almost don't have enough transformations, I would try to figure out the spring constant for the spring in my toaster handle. I couldn't figure out the spring constant for the spring in my toaster handle. I could be boring and tell you about all the energy involved in the marble at the end, but instead I will tell you about the energy involved in the time that my mom tripped over the toaster cord and knocked everything over, especially the toaster going under the floor, which is what we're focusing on. This is another potential to kinetic transformation, and of course we're using this here formula again. So I found that this toaster is I found that this toaster is 0.540 kilograms, and it was conveniently 1 meter off of the ground when it fell. So I'll use this formula to do that. And I found that V should be equal to 4.47 meters per second at the floor, which is pretty believable because it was actually very loud and woke me up, except that it was probably more because of the work done by my mom's leg on the toaster cord, so I should probably calculate that. So normal walking velocity is 1.4 meters per second, so if my mom was walking that fast, the force is probably pretty low. I would estimate it to be approximately the same as the weight force of these 2 soup cans that I'm holding. The weight force of these 2 soup cans that I'm holding is 6.9 newtons. I'm going to guess that she was tripping over the cord over the distance of about 20 centimeters, 0.2 meters. This gives us 1.38 joules of work added. So our new equation is potential plus work equals kinetic using this formula, and this math, the new velocity is 5.01 meters per second. And yeah, this has been fun, but also it's late, so I'm going to sleep now. Goodbye.